So we make use of techniques which allows to measure dark energy and dark matter in an indirect way. And the two major techniques that we use are actually weak lensing and galaxy clustering.
Welcome to Chelonia Podcast, a podcast about the use of scientific discoveries and of technology applications. We provide the best information on projects participated by Chelonia and many more. My name is Gabriella Bernardi, I'm a science journalist, and in today's episode we talk about Euclid space mission, dark matter and dark energy in the universe, with Dr. Giuseppe Racca, Senior Project Manager at the European Space Research and Technology Center of the European Space Agency. Nice to meet you, and would you please introduce yourself and tell us something about ESA and your role?
Thank you very much, Gabriella. As you said, my name is Giuseppe Racca. I work as a project manager, senior project manager for Euclid in ESA, in the European Space Agency. Working as the European Space Agency as a responsible for a mission means that you are responsible for all aspects of this development until it is on orbit and commissioned, let's say, until you make sure that it really works. And then at that point, my responsibility will be passed to someone else who will take care of the exploitation of the data and so. But for the time being, I'm responsible for the whole of the Euclid mission, which is one of the main science mission of ESA at the moment. ESA is well known to be, let's say, the European Space Agency, an organization with 21 members, European members. We are about 5,000 employees across Europe, and the largest technical center is actually the one where I work in the Netherlands, in Noordwijk, and where we take care of all the technology and the mission development for a wide variety of missions, not only science. Myself, I always worked in science missions, but ESA is really a broad spectrum of all possible space applications from science, telecommunication, Earth observation, navigation, exploration, etc.
Perfect. How did you get interested in physics?
But I have always been interested in physics since I was a kid. So that's for me. I don't really remember when I started. I started being interested in nature, how nature is working since as a kid, as I said. Then in high school, I actually got very much more into physics when I read a book from Introduction to Modern Physics by Leopold Infeld. Leopold Infeld is a physicist working with Einstein in Princeton times, and he had this book which really struck me. I mean, I was really, from that moment, I was already studying some physics in high school, but that was with the modern physics was really something which marked me seriously, also for my decision in the future. Then after high school, I went to enroll in physics at the University of Torino, which is my town. And but I was a bit disappointed by the confusion that there was in the registration. So then I said, okay, I better go to the Polytechnic of Torino, that is an engineering school, renowned engineering school in Torino as well. And then I asked them, can I study physics here? And then and they told me, yeah, of course you can. And the best place is study nuclear engineering. So then I think at the moment it's not called nuclear engineering anymore. I think it's called like physics engineering or something like that. But that's at the time it was. So then I enrolled there and I studied there. And I think in the end it was a good, let's call it compromise, because together with a solid basis of physics, it also gave all the engineering disciplines, which in the end it was quite important in my future work.
Okay, perfect. So the standard model explains just the 5% of the mass and energy of the universe. So how can you describe the dark matter?
Yeah, dark matter actually is quite surprising that dark matter it's a pretty old concept. Let's say it's nearly one century, because Franz Zwicky was the one who started talking about hypothesizing dark matter to explain the excess of let's say the excess of rotation of the galaxies of the Coma cluster. It was in the early 30s, so then it's actually 90 years that let's say people think about there must be something there that we don't see. The definition of dark matter is pretty simple, in the sense that it is something that interacts with the gravity. Let's say it interacts through the force, one of the four forces, that is gravity, but does certainly not interact through electromagnetic forces, because we don't see anything and we don't see absorbing anything, and probably also not with the other weak and strong forces. Although, let's say, one of the candidates, these WIMPs, but actually WIMPs, W stands for weak interactive massive particles, so then that was indeed supposed to interact with weak forces. However, this one, which were a few years ago like a good candidate, are not really being found, despite there are a number of searches for that. So what is actually dark matter? I would say it's darker and darker. I mean, nobody really knows. And there are, of course, all these news, let's say, as you said, let's say the standard model as it is does not predict that, but you know, there are this extension of the standard model, these supersymmetric particles, which could be candidates of dark matter. But indeed, dark matter simply says something which is subject to gravity forces and apparently nothing else.
Exactly. Can you explain the Euclid mission, or in other words, how it will help to address the dark matter and dark energy problem?
Okay, Euclid, in a very simple term, is a very precise observatory in the visible and near infrared. So then it only observes things which are observable. So then it does not observe directly dark energy or dark matter. Therefore, all our measurements are indirect. So we make use of techniques which allows to measure dark energy and dark matter in an indirect way. And the two major techniques that we use are actually weak lensing and galaxy clustering. Weak lensing is basically exploiting the fact that the shape of the galaxies, the far distant galaxies from, let's say, outside our own galaxy, are distorted by the presence by both the presence of matter that is in between the observer, ourselves, and the source, the galaxy itself, and it is distorted by the presence of dark matter, and in combination with the expansion produced by the dark energy, it produces a certain distorted image of these galaxies. Galaxy clustering is instead another parallel probe, and the beauty of Euclid is that it does this at the same time in the same field, and this is very important. And galaxy clustering, instead, the way the let's say position and velocities of the various galaxies, how they get together and what velocity they have with respect to each other, which also measures the combination of growth and growth that is due to the combination of gravity and expansion due to the expansion of the universe itself and the additional acceleration by the dark energy. By putting all these measurements together using cosmological models, which are also based on other missions, altogether it gives a pretty good picture of what the dark energy is, in the sense of finding whether it is really only a cosmological constant, like even Einstein had already predicted at a certain point, or if it is the energy of vacuum, therefore something which is intrinsic with vacuum and not changing, constant, or if it is instead a kind of quintessence, as they call it, that is a field which may have changes during time, even though slow changes during time. And Euclid will actually be able to investigate that. In addition, dark energy could actually be simply a result of a not correct application of Einstein general relativity at large scales, like the cosmological scales. Let's say if general relativity does not apply at that scale, it could make a kind of effect that is that we interpret as dark energy. And Euclid has also, in particular, by the way, Euclid is called Euclid also because of the father of geometry, Euclid himself from Alexandria, because the gravity and geometry of the universe are very much interrelated. And so Euclid will really, has one of the experiments is indeed to measure this growth of structure, of large structures, in a way that can distinguish between the effect of a failure of general relativity to describe correctly the gravity, and instead at the presence of an external field like a quintessence or a cosmological constant. So we'll have this feature, which is very important.
Impressive. Yes, can you tell us something more about the challenge of building a satellite like that?
Yeah, the main challenge is, I would say, in all what is called wide field cosmology, is that it's a precision measurement. Let's say all these effects that we are not discovery measurements. Let's say it's not like, searching for gravitational waves. You detect the gravitational wave, and that's a discovery. Instead, here there is not something we need to detect, because what we look at are new features, but are not new in their own nature. But we need to make these measurements, both the shape of the galaxies and the position and velocity of the galaxies themselves, in an extremely precise and unbiased way, because Euclid will measure really a huge amount of galaxies, which is actually in the order of several billions of galaxies. So then it's really a huge amount. So then the statistical aspect is well covered. Let's say we measure enough to remove all the statistical errors, but if we make systematic error, if we are biased, then all what we measure it was nothing. So then we are constantly challenged by this. And every measurement we make, we always have to make sure that systematic errors are not killing the objective of what we want to measure.
Now we are curious, what were your biggest success and failure in your career?
To be honest, I don't know, because it's not something that I look at. Let's say neither at the failure nor at the successes. I really honestly, I don't know. I believe it's let's say I take the life as it is, professionally and privately, without really looking too much at what has been a success and what has not been, or what has been a failure, to be honest.
Okay, what keeps you excited and makes you want to start working in the morning?
Really is to get my job done. Let's say I think I'm busy with a great endeavor that this last one, Euclid. I'm on this project for 10 years already, and I really can't wait to see that all problems are solved, because we still have a number of problems, and see these satellites flying and bringing back the results, and to give a really a very good contribution to this part of science, to cosmology. I really can't wait for this, and this really would push me every day to keep struggling in the small issues that we have all the time.
Okay, and now, Dr. Racca, what is your biggest challenge right now?
Yeah, it could be surprising, but and it may even sound somehow trivial, but it's really all about small issues. Let's say it's a lot of incredibly difficult small issues to solve. For example, I tell you one that I was busy just before this call. We have a pressure regulator in one of the system of which maintains the telescope very, very well pointed. There is a micropropulsion system that is called, which uses gas under pressure, and you have pressure regulators to maintain the pressure at a certain level, because you need to really be able to thrust really very, very slightly to maintain the pointing. And we have failed, these pressure regulators failing all the time, and we keep changing them and they always fail. So it seems a trivial thing. Let's say pressure regulators, you have them everywhere, from your scuba diving bottles to everywhere in every plane, etc. But for some reason, we cannot solve this problem yet. We also have other parallel problems in other instrument. We have an instrument which has a power supply problem, and also this one we have been struggling for that for months already, and we cannot solve it. Of course, the other challenge I was talking about, let's say the most important one, the fact to maintain the observation bias free, is always something which keeps our level of alert always very high. But I can tell you the main challenges are really small things, and they happen all the time while you are at the end of the construction of a big system like this one. Or also in the data processing, we have also there challenges in the, for example, we need to use graphics processing units now for some of the pipelines to reconstruct some of the data processing. Also, that it's a big challenge, because you may know there is a shortage of CPUs, and let's say simply procuring those, it's an issue. So,
if you could go back or forward in time, what would you like to know or discover?
If we go forward, for sure, I would like to understand if dark energy is a real thing, or is just an effect of something else like gravity, etc. And also the completeness of the standard model. It's something that also I'm really very curious, because standard model was actually, let's say, when I was studying, standard model was still an active research field. So then I did not really study it. So then because I just got involved more later on. But it seems it is a fantastic achievement. And now, if this is not really explained in the full picture of the physics we have around, it's very unsettling. So then, and it seems to be like that. So then, whether we need to have the supersymmetric particles or not, I think it's something very important. Instead, if I look back in time, what I would have really liked to work with is with Lagrange. That is another, is a guy also in our Torino, and later in everywhere else. I had read once that he was disappointed that he was born after Newton, because he said there is nothing to discover anymore. But in reality, if you read Newton's Principia, you don't understand anything. Instead, if you read Lagrange, Lagrange is the one who invented mechanics the way we know it, and he and Euler, etc. Let's say the three-body problem. For me, I was fascinated by these equations that he wrote. I think Lagrange is really, I would have liked to be a pupil of him and working with him. That's for sure.
Fantastic. Last curiosity, what do you do outside your job for fun?
Let's say my great passion has always been mountains. So then I have been doing mountaineering. I've been doing rock and ice climbing and skiing, and now I do it less, but I still do it. I was climbing also a couple of days ago when I was in Italy for my work. And whenever I have been traveling in the world, I've always been looking for mountains and places where to go. Let's say from hiking, climbing, and skiing, and so. I like sports in general. I also like tennis and golf, and I like music a lot. So I'm quite attached to my progressive rock of the 70s. That is the music I grew with. But I also like a lot classical music, romantic music from Beethoven to Rachmaninoff. These are my favorites.
Thank you so much, Dr. Racca, for joining us today at this podcast, and thank you, our listeners. If you have any question about today's show, you can get in touch on Chelonia Twitter, and feel free to subscribe Chelonia.Swiss website and be part of the community. In meantime, stay tuned for our next interview. Thank you.
Thank you.